Okay, so I'm not a roboticist. I work on algorithms, and in particular, I've been working a lot on reinforcement learning algorithms. I think the paradigm these days doesn't really need an introduction anymore, but for the purpose of the workshop, I think it's perhaps useful to remind ourselves why RL is exciting. Okay, so RL in principle, powerful because we can specify the objective, not the solution. The problem, I guess, in practice, this was already alluded to in the introduction, is that especially in embodied settings, it's not always easy to express the goal of the learning process well. And as many of you have probably experienced, reward design can be extremely hard. For instance, designing a good reward for jumping ended up causing us quite a significant headache in the past. And in other cases where we had more luck, for instance, here where we designed simple rewards, where things worked well when we had simple rewards and put simulated creatures in very diverse environments, and that also had some curriculum structure, where in this case RL discovered complex movement strategies, both for simple but also for more complicated bodies. Even in these more successful cases, we found that the learned movement strategies exhibited undesirable features. So, for instance, in the videos at the bottom, we can observe the distorted upper body poses of the humanoid. But in other situations, we saw much more awkward solutions, even in this sort of successful case. So, what these two examples illustrate is that even though RL can discover complex movement strategies, in some cases even from scratch, this is true only as long as we have a good objective and we can structure the learning scenario appropriately. And but as RL is now going to be used more increasingly widely to tackle difficult problems even in the real world, this raises some questions. For instance, what is a good reward and curriculum for complex long horizon tasks? How do we specify the desiderata that are often important, such as gentle, human-like, or natural? And as we work with real robots, how can we ensure safety of the final solution or of the learning process, for instance, during exploration? And how can we improve data efficiency and avoid relearning solutions, especially as we move for more complicated and towards more complicated lifelong learning scenarios? So all these questions, as already alluded to in the introduction, motivate the development of methods that allow us to either inject prior knowledge into the learning process or allow us to transfer knowledge about solutions from tasks that we've already solved to new settings. No. All right. So luckily, modern algorithmic frameworks give us ample opportunity to inject prior knowledge into the learning process. Most modern, especially off-policy learning algorithms, separate acting from learning. This is shown on this slide here, where on the left-hand side, we have the actor interacting with the environment, collecting data that goes into a data buffer. And on the right-hand side, we have a learner that optimizes the policy following for some objective of also the value function. Importantly, in the off-policy setting, the actor on the left doesn't have to optimize for the same objective that the learner optimizes for on the right. And this allows us to modify, sort of play with each side separately as we're trying to inject prior knowledge. And accordingly, we can broadly distinguish between approaches that affect data collection and those that affect the learning process or the objectives themselves. For data collection, we can inject prior knowledge into the actor process in a number of ways. This can be the use of carefully designed exploration strategies, handcrafted controllers, a learned expert policy, or even a human teleoperating system. And on the learner side, we also have multiple choices how we can influence what's being learned. For instance, we can reuse previously learned handcrafted policy components to represent the new policy that's being learned. And this has been extensively explored in the literature, for instance, skill reuse, or as mentioned before, in the form of residual controls. Alternatively, we can bias the learning outcome.
I gotta minimize this. How do I do that? There we go.
We can bias the learning outcome by modifying the objective function. For instance, we can use additional regularization terms that keeps the learned policy close to some expert's behavior. An example here is HAL regularized RL, but there are many others, such as adversarial imitation learning, adversarial motion bias, etc. So this cartoon illustrates how I like to think about behavior bias in this context. With plain RL, we need to search the full trajectory space for the reward. And if the reward admits multiple solutions, then we have no control over which solution the algorithm will find. In this context, the behavior prior that favors a particular region of the solution space can have one of two effects. It can either simplify the search by restricting it to the favored region, and if the prior is appropriate, it can speed up work. It can also simplify reward design by restricting possible solutions to the intersection between the rewarded region and the region favored by the behavior prior. It allows us to be less careful when designing the reward. We can think of the three classes of approaches from the previous slide in the schema. Policy priors for exploration only change the way we collect data, and hence search for the solution and hence how we search for the solution, but they don't necessarily constrain the solution directly. Data collection is sort of limited in this picture. Data collection is limited to the shaded area, but the final solution can lie anywhere in the rewarded region. In contrast, a fixed set of skills that we pre-train and then reuse in a target task usually affects both the exploratory behavior of the target policy that's being learned, but also changes the solutions that can be learned. In this cartoon view, search is limited to the shaded area, and the solution is restricted to the intersection between the shaded and the red area. And finally, policy regularization does not modify the policy directly or the exploratory behavior. Instead, it changes the objective function to favor solutions that are compatible with the prior's preferences and with the reward. Search, in principle, can occur anywhere in the trajectory space, but the final solution is more likely to lie in the intersection between the shaded and the red area. And unlike with fixed skills, which often pose a hard constraint, regularization often does not, but can instead achieve sort of a favorable trade-off between reward and similarity to the prior. So what I want to do in the rest of my talk is that I will give several examples of uses of different types of behavior priors, either for learning behaviors for real robots or for complex simulation tasks. The first example is a behavior prior in the form of hierarchical skill reuse. And this work was originally motivated by the desire to create general purpose motor modules that would allow us to solve complicated log horizon tasks for simulated characters, such as shown here on the slide. More recently, we've also used the same idea with some adaptations for real robots, and this is what I'll focus on in this talk. So RL has recently been very successful for legged robots, in particular for via sim to real. One challenge that sort of recurs in the setting is that of behavior regularization, which often necessitates carefully tuned reward functions to get safe and sort of pleasing behaviors for the robots. What we wanted to study here is whether we could create a general purpose motor module derived from motion capture data that could then be used to learn many downstream tasks where with sort of simple rewards that focus effectively on task success only. So the pipeline that we used for this was an adaptation of a pipeline that we had originally developed for simulated characters, and it consists of 4 steps. So the first step is to retarget a moderately sized set of motion capture data of appropriate type to the robot. So we've done experiments with 2 different robots, a quadruped and a humanoid, and we use dog motion capture and human motion capture data respectively. In the second step, we then train a goal-directed imitation policy. So the policy consists of 2 components. There is the high-level imitation policy, which at every point in time, so the policy is trained to track the motion capture trajectories, and at every point in time, the imitation policy encodes the next desired pose of the robot into a latent action or latent goal space. And the second component is a low-level controller that takes the current state of the robot, its pose, etc., and the desired future pose and translates it into an action. So you can think of the latent action in this case as a desired goal in pose space. And to ensure that this latent action space is well shaped, we regularize it against the prior, which in this case is an autoregressive Gaussian. So once the policy is trained, it can be used to do, for instance, zero-shot imitation of a motion capture trajectory using, as is shown on this slide. So this policy imitates the motion capture trajectory that's indicated by the stick figure. And you can see that the robot tracks it pretty closely with the general purpose imitation policy. Once the imitation policy has been trained, in particular the low-level controller has been trained, we can reuse the low-level controller as a motion prior for other downstream tasks. During that phase, we train a new high-level task. So we throw away the imitation policy. We train a new high-level task policy. That task policy is sort of trained with a simple reward function, and it chooses actions in the latent action space. The low-level controller is held fixed during that task, during this training phase, and we still regularize towards the prior because this sort of facilitates exploration. And what you can see on the left, so this shows examples for a couple of tasks. On the left-hand side, we train joystick controllable policies for both robots, both for the quadruped and for the biped. And these are pretty reliable, especially for the quadruped. And move quite fast, but maybe not so visible in this video, in agile ways. And on the right-hand side, we use the same motor module to train a different task, in particular a dribble task, where the robot has to move a ball towards a target. You can see this both in simulation and in the real world. And you can see that the robot has developed some rather sophisticated strategies, kicking the ball with its hind leg in a quite deliberate manner. So the same motor module can subserve multiple downstream tasks, and in all cases, during reuse, the reward that's used to train these tasks is very simple, and we don't have to worry about any additional regularization terms. Okay, so this first example has demonstrated how we can learn motor skill modules that constrain robot behavior to be naturalistic and safe. And that can be reused to solve many different tasks without having to worry about careful regularized task reward design to achieve sort of acceptable solutions. In the second example, I will focus on how priors for regularization exploration can be used to learn complex tasks directly on a real robot. The study was conducted by some colleagues of mine, and it was motivated by the task shown here on the slide, which is a benchmark released by colleagues from DeepMind. The task requires the robot to stack a red object on a blue while ignoring a green destructor object. And what makes the task challenging is that there are many different object shapes, and the robot basically needs to learn and understand how to stack these different shapes in a stable manner. The task is made further difficult by the fact that there's a training set and a holdout set, which sort of allows us to measure generalization and adaptation performance. So the task is difficult to solve directly on the robot for several reasons. There are exploration issues, and it also requires perception, makes it hard to learn. It's also difficult to solve with pure sim to real because of the inevitable mismatch between sim and real, both perception and dynamics, but also because the task ultimately requires adaptation to the holdout objects. My colleagues therefore pursued a mixed approach, where they first trained a policy on the training objects in simulation, and then they used this as a prior when training a new policy directly on the robot. For this study, it was important to be able to deviate from the prior, to achieve improvement over the imperfect sim prior in the real world, and also to achieve generalization to the holdout set of objects. So basically being able to deviate from the prior is really what's important here. So the approach therefore uses the simulation prior in two ways: to affect both the data collection and to change the objective. First, they use the simulation prior for exploration. So they bootstrap learning by pre-collecting a data set of a certain size by executing the simulation prior policy on the real robot. The initial data collection is then followed by an online phase where the policy was executed that is being learned on the robot during learning to enable further data collection from this online policy. And importantly, during this online phase, the policy learned the simulation policy is also used as a prior for regularization to stabilize the learning, improve learning. To make it easier for the sort of learning process to eventually deviate from the prior, they set up the prior that they were regularizing towards in a particular way, but this goes beyond sort of the time I have in this talk. So they conducted a careful ablation and found that both aspects or both uses of the prior were essential. Just using the prior for exploration would collect good data, but making use of this data would be difficult because it's quite off policy. Just using the prior for regularization would incur a high cost because regularization kind of requires you to transfer the prior behavior towards the student policy. But this requires quite a lot of upfront data, especially since the uninformed sort of student policy doesn't explore very interesting states. Pre-collecting the data by executing the prior gives the data sets on which the prior can be, so the prior behavior can be effectively transferred to the student policy. So some of the results are illustrated in this plot. The dashed line shows the performance of the simulation prior directly. The blue line is a policy that's learned using an offline RL algorithm from the data collected by the simulation prior. You can see sort of that performance saturates despite sort of a growing data set size. And the orange, green, and red curve show training with the full system using the simulation prior, both for exploration and regularization, starting with different initial data set sizes collected by the simulation prior. We can see a clear improvement when the prior is used for both exploration and regularization, over just a zero-shot transfer to the real world, and also over using the simulation prior just for exploration. And the study contains a careful ablation that shows that all of the components are actually needed. I encourage you to check it out if you're interested in this. Okay, so I've shown two examples of different types of behavior priors. I've shown how a skill module can constrain robot behavior and how a prior implemented via regularization and exploration can effectively kickstart learning and allow further improvement when learning on the real world. Both applications that I've shown so far, however, sort of demonstrate how priors can be used to learn relatively simple short horizon tasks. In the last example, I want to demonstrate how we can combine multiple priors to obtain complex long horizon behaviors in simulation. So the test environment for the task for the study was a form of simulated soccer. And soccer is extremely rich and poses a number of challenges requiring short-term motor control, but also longer horizon planning and coordination. So we can think of soccer in terms of three levels of abstraction. We need robust and dynamic low-level motor control. We need mid-level goal-directed soccer behaviors, such as dribbling and shooting. And we need some form of high-level planning to decide where to position yourself on the pitch, how to coordinate with your teammates, and how to sort of respond to the behavior of your opponents. In the context of this talk, so if this entails two interesting questions. The first one is, how can we specify structure at different levels? And how can we represent this structure in a reusable manner? So solving the task with end-to-end RL, even though we had sort of success with other multi-agent scenarios before, here was very difficult. We therefore pursued a strategy that sort of consisted of three components. Firstly, we used a form of gradual skill acquisition. So our agents first acquired some low-level movement skills. We then endowed them with mid-level soccer skills, such as running, turning, dribbling, and kicking. And finally, we trained them to pursue goal-directed and coordinated soccer gameplay. We also used multiple learning signals. So we used imitation learning for the low-level movement skills, reinforcement learning with sort of a well-defined reward function for the mid-level skills, and then multi-agent RL and self-play for discovery of complex high-level strategies. And thirdly, we used two types of explicit skill representation that allowed for efficient learning without restricting the flexibility of the final behavior. To constrain the movements of the soccer players to serve towards natural human-like movements, we used the general-purpose low-level movement skill module that I've introduced before. And we then used behavior priors for the mid-level skills to give the agent to bias the agents towards sensible soccer behavior, but also give them the flexibility to discover new behaviors as needed. So this gives an overview of the entire pipeline. Don't worry about parsing the entire diagram. I'll talk through it in a second. But basically what you can see is that from the left to the right, we start with learning the low-level skills, then move to mid-level skills, and finally do multi-agent training to discover the high-level, the complete soccer behavior. So the first the first training phase is the training of the low-level skill module, which you've basically seen. It's basically the same as what you've seen in the first part of the talk for the robots. So we had a bunch of dedicated motion capture from free soccer play where the ball was not tracked. And we use this to train basically this motor skill module just in the same way as described before, by basically training tracking policies and then distilling this into a general purpose low-level controller. The skill module induces naturalistic low-level motor control, but does not induce any goal-directed soccer-relevant behavior like interacting with the ball. So to achieve this, we created a set of mid-level skills. For this purpose, we set up a number of training drills that are relevant for soccer and trained policies to solve them via RL, using this previously trained low-level controller for regularization. So the drill specifically that we considered was sort of following a target, dribbling after a target, kicking towards a target, and shooting at the goal. Here are some examples of the policies learned. So this is a goal shooting policy. Hope you can see the ball. And on the left, you see a dribbling sort of policy that we trained. Okay. So we then wanted to use the behavior derived from these drills to regularize the behavior in the full game. To this end, we needed to address two questions. The first one is the drill experts are dependent on some additional context, like a goal, for instance, that the dribble policy needed to follow. The target that the dribbling policy needed to follow. And that goal is obviously not, or this target is not available during soccer play. So we need to get rid of this, or need to get a prior that was independent of this. And secondly, we have multiple different drill behaviors, and we want to regularize the agent at different points in time towards different types of behaviors as appropriate during the gameplay. To address the first problem, we distill the expert policy into prior policies that are no longer dependent on the context. So the context here being, for instance, the target for dribbling or for shooting. The objective for this is shown at the bottom. The effect of this is that the prior policies effectively learn a mixture behavior that is obtained by conditioning on different targets. Graphically, we can think of this as follows. So if you think about each of these colored blobs here as as the behavior that you would get from executing the policy with a particular target location, then the prior policy that we obtain from this distillation objective is effectively a mixture policy that covers all the different goal locations. And the agent, when you execute this policy, will randomly sample a behavior. One important insight maybe here is that by choosing different model classes during the distillation step, we actually get different forms of generalization behavior. And so this is very much like what you get when you choose different models during density estimation. And we can control how this behavior prior generalizes. Okay. So the model class determines the generalization behavior. And just to illustrate what this looks like, so this is the dribble prior. You can see the target moving around, but it doesn't follow the target anymore, and it spontaneously changes direction without being prompted by anything. It changes the speed and so on, right? So you can think of this as a pluripotent dribble behavior. Okay. All right, so this gives us all the ingredient that we needed to train the agents in the full game of soccer. So high-level strategies are hard to handcraft by hand or specify via rewards. This is why we rely on population self-play to sort of discover complex solutions, so the usual auto-curriculum strategy. But in the game of soccer, it's already so we train multiple to sort of obtain robust behavior. We have different agents that we train and play against each other, and they sort of learn to exploit each other and so on. This works vanilla with simple bodies. Here, it doesn't work from scratch, and we therefore use the components that I prepared on the previous slides to shape the behavior during this during the self-play process in the full game of soccer. So in particular, each of our soccer agents produces action through the low-level skill module. And basically what this does is it aids with exploration, and it also imposes a constraint on the behavior of these agents to be naturalistic. We also bias the agent's behavior towards the mid-level skills. And here, sort of as I mentioned before, since these skills are quite specific, but we don't really know what's needed during gameplay, we want the agent to be able to deviate from the mid-level skills when needed. So we do this via regularization. This is just the usual KL regularized objective here. There's sort of a small difference though. Since we have multiple skills, we basically need to give the agent the opportunity to choose among these different skills in different situations as appropriate. So in particular, we want to avoid a situation where the agent follows at all points in time some average behavior described by the different priors. So to achieve this, we construct mixture policy. The mixture policy is shown down here. So it's a mixture of the different drill priors, dribble, kick, and so on, shooting and so on. Okay, so to understand the effect of this, it's useful to look back at a picture similar to what I've shown before. So this picture illustrates the effect of the KL-regularized objective. So the objective favors solutions that lie at the intersection between the behavior favored by the prior and by the reward. This is for a single prior. Now for our mixture prior of multiple priors, the situation looks as follows. If we regularize, so the different colored blocks show sort of roughly the behavior favored by the different priors. If we now regularize simultaneously towards all these different priors, we would basically get a favorable behavior that sort of roughly lies in the middle between all of them, like in the gray region, which is not what we want. So by regularizing instead against a mixture, due to the asymmetry of the KL, we get an effect where the agent can effectively or is effectively just regularized against the closest mixture component. And so can adaptively choose which one is the most appropriate behavior at any point in time and ignore the others. Okay, so here are some highlights from the of the agent gameplay after training. And there are clearly some features that don't look very realistic or very nice. They're sort of like when they fall and try to get back up. But there are other parts of the behavior, like very robust sort of jostling, how they interact with the ball, that are actually quite impressive. And the agents also clearly learn to pay attention to each other. So with maybe just two players, you don't get very sophisticated. That's right. Let's let this play for a second. Okay. So yeah, this is basically the end of my talk. Just to summarize, I've discussed sort of different versions or different sort of broad approaches of behavior priors and how they can be used and what effects they have. And then I've given 3 examples. I first discussed an example where the prior is used by a hierarchical skill reuse. The specific prior is a skill module learned from motion capture data, and we've used it to induce naturalistic movement skills for a robot, which can then be used for different downstream tasks. In the second example, I've discussed how a prior can be used by exploration and regularization. The prior policy was trained in simulation, and I've shown how this enables efficient real robot learning. And in the last example, I've discussed how multiple priors can be combined, doing both skill reuse and regularization to obtain sort of complex multi-scale behavior. The 2 skill modules were a low-level skill module for motion capture data and mid-level skills that were trained by RL. And yeah, so that's basically it.
Thank you very much.
Actually, let me say one more thing without going through the entire slide. even though I have sort of introduced skill reuse and regularization as sort of different ideas, so they can really be motivated from the same principle, also sort of more formally.
Perfect. All right. Thank you very much, Nicolas. Do you have any questions of the speaker? Please come up to the mic so we can take this on. And if you're online and you have a question, please raise your hand or type a question to the chat.
Thanks for the presentation. In your first part of your talk, so you showed a dog moving around, which you're trying to learn a domain agnostic motion module, and then for the downstream task, you would fix the motion module and just train for the high level policy. Is that right?
Yeah.
So what I'm surprised about is that in the low level skill module acquisition, motion module acquisition, there was no kicking involved. It was just sort of walking around. But yet when you were training for the kicking task, it somehow figures how to kick the ball, even though that was not seen during training. And I would assume that the motion commands for kicking is quite different from just motion commands for generally walking around. So could you just speak to that?
Yeah, so sort of one of the kind of design ideas behind this, the training for this motor module is basically to, I guess, find a good trade-off between specificity and generality. So it doesn't try to imitate sort of entire, like even, it doesn't really try to directly imitate sort of movement segments, but I guess it's a bit hard to articulate, but you can think more of it as a set of basis functions that you can recompose in a flexible way. There are obviously limitations to the kind of behavior that you can produce when it's not in the motion capture data, but it allows you to basically recompose movements in different ways, even though when they were not exactly seen in the training data. And I think this is sort of a consequence of the regularization, but also of the very sort of short horizon tracking objective that we're using. The price that we pay for it is that basically some of the knowledge needs to be imposed in how you choose the sequence of latent commands that you send to the low-level controller. And this is sort of I haven't shown this here, but we have a prior that's temporally correlated, which biases you towards a particular sequence of high-level commands to be sent to the low-level controller. In the soccer example, we train sort of these mid-level priors to produce particularly sensible sequences. Okay, so it's a trade-off. The low-level controller is designed to be quite flexible, which requires us to then sort of inject more knowledge during reuse.
Yeah, so in the soccer example was slightly different because in the motion capture system, we've had examples of the ball kicking, which was, I was not surprised with that, but the dog kicking the ball was quite simple.
No, I understand. I think it's probably a case that in the motion capture data that we have, that there may be this type of leg movement, but that in a different context. And then due to the way the system is trained, it can sort of repurpose that movement that was somewhere present in this new context.
But is it fair to say that there's limitation to how much of it can be composed if the amount of data is far deviates from what was seen as motion capture?
Yeah. So if in the motion capture data the leg is never lifted up here, for instance, then probably that will not work during reuse either. Yeah, and if also for as a specific point in case for the soccer, for instance, we did previously or initially train the motion module for soccer with sort of, I think, just the generic CMU motion capture database, and the results were less agile and aggressive than we got out. Yeah.
We have time for one more question from the audience or online.
Thanks for the talk. That was really fascinating. So I don't work in RL, but I find the whole prior thing really cool. Just, I guess, less of a technical question on the complex sort of stuff with the mid-level priors. Was there any behaviors that there was one that you found particularly surprising? Because I guess soccer is a very specific thing, and like in real games, you might do things which are counterintuitive to your goal, like in order to trick a defensive play, you might run one way and then back the other. Did you find that your agents were able to learn anything surprising like that?
So they didn't really learn very surprising high-level strategies like what you're describing. I think there are still some limitations to, so they did learn to pay attention to each other and to, for instance, not all rush to the ball, but if one of them goes to the ball, the other one will move forward or they fall back to cover the space, but they didn't learn sort of something like what you're describing. And they also didn't learn to dive because I think we didn't have the right tools for this. But what I was surprised by is sort of more of some of the motor control that they exhibited after the multi-agent training. So if you look at I guess you've seen sort of examples of the mid-level priors, right, that I was showing, and they were kind of agile, but relatively stereotyped also, right, like how it dribbles the ball and how it kicks. But after multi-agent training, I think the behavior where it kicks the ball with the outside of the foot, or the stability that it exhibits when it sort of jostles with its opponent, that's sort of something that certainly wasn't induced by the mid-level skills, but was then discovered during the multi-agent training phase. So on that level, yes, but not on the higher level that you're describing.
Thanks very much.
Perfect. All right, let's thank Nicolas again for this fascinating talk.